Good morning. My name is Johansson and my register number is URK25CS1018. In this video, I am going to explain three practical applications of the inverse Laplace transform in computing systems, along with the mathematical concept and how the Python program performs the computation. The inverse Laplace transform is a mathematical technique used to convert a function from the Laplace domain, which is represented using the variable s, back into the time domain, represented using the variable t. This helps us understand how a system behaves over time instead of in an abstract mathematical form. First, let us consider network packet delay analysis. The given Laplace domain function is 1 divided by s plus 5. When we apply the inverse Laplace transform, we obtain an exponential decay function which is e power minus 5t. Mathematically, this represents a standard form where a constant added to s results in an exponential delay in time. In the Python program, we first import the SymPy library, which is used for symbolic mathematics. Then we define the symbols t and s. After that, we define the function in terms of s and use the inverse underscore Laplace underscore transform function to convert it into the time domain. The result includes a unit step function, which is automatically added by SymFile, and we remove it for simplicity. The final output shows an exponential decay, indicating the packet delay decreases rapidly over time. For the next one, we look at CPU load response in cloud computing. The given function is 4 divided by s squared plus 16. When we apply the inverse Laplace transform, we get a sine function, specifically sine of 4t. This follows a standard mathematical result where expressions of this form produce sine outputs. This indicates oscillatory behavior in the Python code. The same steps are followed: defining symbols, writing the function, and applying the inverse Laplace transform. The result is a sine wave which shows that CPU load increases and decreases periodically, reflecting real world fluctuations in processing demand. Finally, we consider data transmission signal reconstruction. The given function is 2 divided by s squared. When we apply the inverse Laplace transform, we obtain 2 times t, which is a linear function. Mathematically, this corresponds to the property that 1 over s squared into a linear time function. In the Python implementation, we again define the function and apply the inverse transform using SymFile. The result shows a steadily increasing function representing how data accumulates over time during transformation. In all three programs, the key states are importing the SymFile library, defining symbolic variables, expressing the Laplace domain function, applying the inverse Laplace transform, and simplifying the output by removing the unit step function. To conclude, the inverse Laplace transform helps us convert mathematical models into time-based interpretations. Through these examples, we understand exponential decay in network delay, oscillatory behavior in CPU load, and linear growth in data transmission, all of which are important in analyzing real-world computing systems. Thank you.